Hello and welcome to this video on iteration. Now this is a GCSE grade 9 topic, and what I've done here is I've created a question that might be a bit like the GCSE question, but I've extended it with part B by making it slightly more difficult, but it does make for a very interesting overview of this whole topic. So iteration is a process used to find solutions to equations which can't be solved easily by normal algebraic methods. So for example, this equation here, if this was a quadratic, we would solve it using the formula or completing the square or factorizing. Okay, but we can't really solve a cubic in that way. And we can find approximations to the solutions using iteration, but they are remarkably accurate. And this is how it works. We're told, first of all, to take this equation and arrange it to give this. Okay, so we'll do that first, and then I'll explain a bit more about how the iteration process works. Okay, so to set off, I'm going to simply do what part A asks me to. And I'm going to say that 2x cubed, okay, if I add the 5x and the 1 to the other side, I'm going to get 2x cubed equals 5x plus 1, okay? And then if I divide both sides by 2, I'm going to get that x cubed equals 5x plus 1 all over 2. Okay, and then I'm going to cube root both sides to get x on its own. Okay, now the way that we can write that is we can write a cubed root sign, okay, or we can put it to the power of 1/3, which means the same thing. Okay, so I'm going to do that. I'm going to write x equals this expression here that we've just written. Okay, so this thing here, and if I just make a copy of that and bring it across, 5x plus 1 over 2, and all of that is going to be to the power of 1/3, which is the cubed root of it. And that is the result we were required to prove. Okay, so that's the first part of the question answered. And if you couldn't do the rest of it, at least you've got a mark or two for that first part. Now it says, hence, that means using this result, find 2 of the solutions to this equation to 3dp. And then we're told later that there are 3 altogether, but we're going to find 2 of them, and this is how it works. I've plotted the graph of the original equation here. Okay, 2x cubed minus 5x minus 1, y equals that. And you can see that the 3 places where the graph crosses the x-axis, in other words, where the y value equals 0, is at negative 1.47, negative 0.203, and 1.673. Okay, so they are the 3 solutions that I'm going to find using this algebraic process. So the graph is just there to sort of reinforce what we're doing. Okay, so I'll just move that to one side. Now, what I've done effectively here is I've written this as a function of itself. Okay, I've written it as a function of x by moving part of it to one side and keeping the x on the other side. And what I'm now doing is considering the graph of y equals this, okay, 5x plus 1 over 2 to the power of 1/3, and then the graph of y equals x, and where those 2 graphs cross will be the same 3 solutions. And to illustrate what I mean, I've done that here. So the green line is the graph of y equals this function here, or this one here, okay? And the blue line that's dashed here is the line y equals x. Now you can see that the three crossing points are the same x coordinates as our three solutions that we're looking for, minus 1.47, minus 0.203, and 1.673. Okay? Now, the iteration process works like this. In practice, what we do is we get the calculator, and before we do that, actually, I'll just show you how we write this down. So we start by saying a better approximation of the root n x n plus 1, okay, is equal to the previous value put into this function, 5 times xn plus 1 all over 2, okay, and that is raised to the power of a third. Okay, that's what we call the iterative formula. And what that means is if I take a value of x that's approximately right for the root, okay, times it by 5, add 1, divide by 2, and get the cube root, I'll get an answer. Now, if the iteration is successful, that answer will be slightly closer to the root, okay, and then I repeat the process, and I put that answer back into this equation and do it again, and that will get me even closer. And gradually it will close in on the true value of the root. Now, to set this up in the calculator, we start by choosing a value of x close to where we think one of the roots is. Now, very often the question will tell you what to start with, and we call that value x1. Okay, x1. And we're going to start by choosing the number 2, okay, because we know that one of the roots is 1.67, which is close enough to 2 to make this process work. Okay, in fact, we could probably choose a much bigger number and it would still come in on the root. But let's have a look what happens. So in the calculator, this is how I operate this process. I don't have to keep typing the formula in. So I go to the calculator, switch it on, and literally type this in. 2 equals will store an answer in the calculator of 2. And then I apply this. I put 5 times answer plus 1 over 2 all to the power of a third. In other words, I type that in and then I press the equal sign. And what the calculator will do is it will put 2 into this equation instead of answer and give you the output. And that is what we call x2. Okay, and that will give us a value on the calculator closer to the true root. And then we must write that down usually to 5, 6, 7, 8, or even 9 decimal places. It normally asks you to do at least 6. Okay, and then we press equals again, and it will take that answer and put it back in and give you the next one, x3, and so on. Now, to save time, I've gone through this process already, and this is what happens for this first iteration. So x1 was 2. I'll put that over the top of this here, okay, and I'll just move this down out the way. Okay, so x1 was 2. I'll just take that stuff out of the way. Okay, so, and as you can see, it goes closer and closer to the root. And after about the 4th or 5th iteration, it's starting to look like 1.673. Okay, and if you carried on pressing equals, many times it would indeed give you 1.67 to 2dp, 1.673 to 3dp. Okay, so that has been a successful iteration. Now, if you took the same function, the same iteration, but started with a different value of x1, okay, in fact -1, okay, the same process leads to a different solution here, okay. And if we go back to our graph of the actual iterations in action, you can see that this iteration was closing in on this route here, and this iteration was closing in on this route here. So we found two of the solutions using this iteration formula that we were given in the question. Okay. Now I'm going to explain on this one exactly what's going on. Now let's just look at this bit around 2 here. Okay, so I'll just put that to one side, because what I've done is produced a very magnified version of that part of the graph up here. Okay, you can see the 2 there, and this is how the iteration process has worked to give us this answer here. Just watch this. So I start with a line at 2. So my original x value is 2, okay? And it comes up and we hit the curve here at this point, okay? We then take this line across here and hit that straight line there, the line y equals x, because remember, we're almost swapping the x for a y when we draw this line y equals x. And then we come down when we bounce off this line and hit the curve again about there, okay? And then we bounce off the line and we come in and hit the blue line again there, okay? And then we drop down and hit it there, and then we come across there, and you can see what's happening. It's like ever decreasing steps that are homing in on that solution, and that's if the iteration is successful. Now the lines have to converge together, you see. If they were diverging, your iteration could be getting wider and wider and further away and never reaching the root, but just going off to infinity or something. Okay, and that's the process of iteration. You can get other situations where it sort of spirals around and closes in on the root. Okay, so I've explained how the iteration process actually works on a graph, and it can converge very quickly to the result that we want. If I just clear that off now. Okay. Now, how are we going to continue with this question? Because it's making reference to a third solution. Now, we know there is a third solution because we've already seen it. If we go back to our original graph, we know that there are 3 solutions. And we found this one and we found this one. Okay, but we haven't found this one. And if we try to put any number into this iteration here, it will either default to this one here or this one here. It will not go to this one. And sometimes there's no way of really knowing whether it will or not. But what we've been asked to do is to try another solution, another iteration. Okay, so I'm just going to put these to one side and I'm going to show you how this might now work. Okay, so another iteration might be something like this. So I'm going to start with my original equation, but this time I'm going to take out a factor of x from the first 2 terms. So my original function here can be written as 2 as x times, okay, 2x squared minus 5. Okay, and I can set that equal to 1. So what I've done is I factorised out the x from here, and I put the 1 on the other side. All right. Okay, so from here what I'm going to do is I'm going to divide both sides by x to give me that 2x squared minus 5 equals 1 over x. Okay, and at that point I could now add the 5 to both sides. So I've got 2x squared, okay, equals 1 over x plus 5. And I'm also going to write that now as 2x squared equals, and it's going to be a common denominator of x if I write 1 plus 5x all over x. Okay, there's quite a few iterations that you can make out of something like this, and it's worth just exploring all the possibilities. Okay, now I want x on its own. There's lots of ways I could do that even from here, but what I'm going to do is I'm going to divide by 2 and then square root. Okay, so from this, if I just go on to the next line, I can now say that x squared equals 1 plus 5x over x over 2x rather, and then if I just square root the whole thing, I can do that in one go. I think x equals, so I've got 1 plus 5x, okay, all over 2x, and the whole thing is square rooted. Okay, so if I just complete that like this, and I'm going to use the proper square root sign this time because it's more recognizable when you write a square root rather than a cubed root. Okay, so that is another iteration, and there are many more, as I said. Now, before we proceed with that any further, it might be worth just looking at the graph of y equals the square root of 1 plus 5x over 2x. And then you'll understand why this iteration isn't a very good one. So let me pull that up now, and it's quite different to what we looked at earlier, and it's here. Okay, now you can see I've also got the line y equals x on there, but the problem with it is that because this is a square root sign, okay, it doesn't go below here, okay, because the square root of something can't be normally a negative number. So the other problem is that therefore that you can't home in on those solutions. So when you take the square root in a function, it will always give you just the positive square root unless you ask for the negative one. So it's kind of incomplete really, and it's not showing us the full picture. And if you do try and do the iteration, because remember we're trying to find this missing root, which is here somewhere, close to 0, if you do try to do that iteration, you get, in fact, you start with 0.5, I tried that, you see, hoping to home in on this one, but in fact it goes back to the one we had originally up here, 1.673, okay, 1.673 to 3 dp. So it doesn't actually work or achieve anything. And that often happens with these iterations. They don't always work. Usually the question will steer you in the right direction, and it will give you an indication of what iteration to use. Okay, so we've explored that and found that it doesn't work. So we'll just mark that with a cross just to say that it doesn't work. Okay, and I'll just take these results out the way. And we're going to try a different iteration. Okay, and to save a bit of time, I'll just quickly show another one. So we're going to try this one now. Okay, and in fact, when we go back to this point here, instead of dividing by x, I'm going to leave the x where it is and divide by 2x squared minus 5. So I get x equals, okay, 1 over 2x squared minus 5. Okay, and as I said, there's many others, but this is the one I'm going to try next. Okay, 2x squared minus 5. So basically, I've gone straight from this here, but instead of dividing both sides by x, which I did here, I'm dividing by this bracket to give me this one. So I can try that iteration and see what happens. And this is where it gets quite interesting, because this time, let me show you the graph for that one. Okay, that's the one that didn't work. This one here is the graph for this iteration that I've just created here. All right, and it looks very different. It's a completely different function. It's got 3 sections shown by these lines here, and you can see once again the same 3 roots that we know exist. One's crossing there, one's crossing there, and one's crossing there. This is the one we found before, and this is the one we found before. This is the one we haven't yet found, but this time we will. Just watch this. I'll show you the results for that. So I'll put that there for the moment and bring in the results using the iteration formula, which I've done here. Okay, so I set that up in the calculator in the same way. I used as a starting point the number 1. Okay, so here, and I found that indeed it did close in on this third root, negative 0.203 to 3 decimal places there. Okay, and you can see the process starting to come together there. All right, so what was happening here, it's not very clear on this scale. I might just make this a bit larger. Okay, and you can see what was going on, but basically I was coming in initially with the number 1. I was hitting the curve down here somewhere. Okay, I was coming across from there to the blue line. Okay, then I was bouncing back up to the curve here, and you can see very quickly it's going to close in on that root, which is in fact what it's done in a few steps. Okay, so that's how the iteration process worked. So sometimes you'll get an iteration, it will give you one of the roots, and that might be all you need to do. Okay, it might say to use a different iteration to find another root. So I've made this question very over the top, really, just to give you an experience of all of this stuff together. Okay, so I hope that was helpful, and take care.